Good afternoon, everybody. My name is Mariana Cano Diaz. This is my first time here in this workshop, so thanks to the organizers for letting me present here. And also I would like to thank my host here in UC-HiPACC, who is Kevin Bondi, which is my collaborator in the SDSS4 collaboration. So I'm going to talk about one scaling relation of galaxies that is very commonly used. I'm sorry. Okay. Which is the star formation mean sequence of galaxies. So this relation, you can see, is based on the stellar mass and the total star formation rate of galaxies. And it basically can tell you in which evolutionary state your galaxy is. So if it's a star-forming galaxy, or if it's around here, probably it's a quenched galaxy or a passive galaxy that it has already stopped forming stars. So in order to characterize it, it's very easy. It's usually you only need a linear fit. And well, there have been many papers out in the literature trying to characterize correctly this relation. And it's also known to exist in several wavelengths and also in simulations. However, in order to build this relation observationally, there are many caveats that we have to take into account. So usually or classically, the way that we can do it is either with photometry or with spectroscopy. But in the past, we only had access to single fiber spectroscopy or to single slit spectroscopy. So take, for instance, this figure here that's from the Asian Sloan. So this little square is the single fiber spectroscopy that is placed in the middle. So you will actually use the spectra from this square in order to classify your galaxies and to classify them as star-forming or AGNs or passive. So you can use maybe a BPT diagram. But what if you have one behavior here, but in the rest of the disk you have another behavior? What if actually just here you have a passive galaxy, but here you have a lot of star formation? Then this may be not very accurate. However, nowadays we have access to IFU observations in which you actually put fibers like here. Every dot here is one fiber. And with one fiber, you can have one spectra. In the end, you have this type of data, which are called data cubes, in which you have a spatial resolution here in this plane. And if you go into the z-axis, you will have one spectra per pixel. So this gives you a lot of information. So the study of the spatially resolved star formation mean sequence of galaxies is something a little bit hot right now. So there are already out some works. So for example, this one is using another survey called Khalifa, another survey called SAMI. And actually, to tell the truth, right now there is not a very good consensus on the slope and 0 point, and not either the scatter. If you want, at the end of the talk, I can tell you why I think this is happening. So the first time that I studied this relation is when I was part of the Khalifa survey. Maybe you have heard about it. So Khalifa is an IFS survey in which they observed 600 galaxies. Actually, that's not very true. They kept on going the observations. So right now they have around 1,000 galaxies that are out and that you can download and use the data. So this was like the first serious effort in order to do a survey of galaxies using IFS technology. So here are the references if you need to know. So for this, when this survey was developed, also the PI, Sebastián Sánchez, had to develop a pipeline tool in order to reduce and analyze this amount of data, which was a really cool job. So what this pipeline gives you are not only the data cubes, but also some maps, like H-alpha flux maps, stellar mass maps, etc. So this is the star formation mean sequence that we derived using the Khalifa survey. So how did we do that? These are integrated quantities. That means that if you have a galaxy that is observed with this IFU, take a look at this picture, you basically have to integrate each of these dots in order to estimate the total star formation rate and the total mass. And why I'm saying this in quotes? Well, because this is not perfect. This has some observational effects, because the Khalifa survey is only observing up to 2.5 effective radius. So if your galaxy or the light of your galaxy exceeds that, then that means that the total star formation rate and the total mass will not be entirely true. So the way that we select the star formation, the star forming spaxels is using this scheme that was introduced in a paper by us in 2016. So the star forming spaxels or galaxies are defined as regions or galaxies that have an equivalent width of H alpha larger than 6 and that are below the Q limit. Those are the blue points here in this plot, while the retired ones are regions or galaxies that have equivalent width lower than 3. So you see here this obvious bimodality. So the blue points are the actual star formation main sequence of galaxies that has been done in the past, and here we called it a retired cloud. So now, if we do the same classification, but now not integrating, but spaxel per spaxel, then what you have here is this. So this is the local or spatially resolved star formation main sequence. So this is 4 kiloparsec scales on average. And as you can see here, well, we just try to fit as we will do here for the global quantities. After that, we try to move on using the MANGA survey because the sample was much larger. So now we were using 1,754 galaxies, which is quite a lot. So of course, and also for the Khalifa sample, we were careful in order not to use very inclined galaxies in order to avoid inclination effects. And so we used exactly the same pipeline that is inserted also for MANGA, which is very convenient. And as we have a large sample, now we were able to classify by morphologies our galaxies in order to study the possible dependence of this relation with the morphology. So this is the star formation main sequence using the MANGA sample that are all these blue points here, and this is the retired cloud. The way to classify by ionization is the same that I already introduced for the Khalifa. So we did the fit, I mean, everything is the same. But now, as I was telling you, we were able to classify our sample per morphologies. And as you can see, when we do that, we see that there is like an observational trend for quenching. So here we are plotting only the galaxies, the contribution from the very late galaxies. And as we move on into earlier types, we see that this star-forming cloud starts to get less populated, while the retired cloud gets more populated. As you can see here, there are a few points here. You may ask, well, why do we have elliptical galaxies that are star forming? Well, the most probable thing is that these are not actually elliptical galaxies, that we are only classifying based on the field of view that we have, but maybe they have this component that we are actually not seeing. So this is a spatially resolved BPT diagram using all of the regions of all of the galaxies. So I am only showing here contours because these are more than 2 million points. So basically, all the blue contours are the star-forming contours. And if you actually plot all of your spaxels in this diagram, what you see here is this. So you may wonder what this red line is. Well, this is the detection limit of MANGA. And this is going to be a very painful thing, as you will see in a minute. So this is the local star formation main sequence for MANGA. Also, is kiloparsec scales on average. And well, I am just basically characterizing this with a linear fitting. Here is another effort done by C et al. 2017 using the same sample. So we can do the same now. We can try to see if there is a dependence with the morphology. And as you can see here, this is also the star-forming cloud. We did it for late-type spirals, then moved to early spirals, lenticulars, and ellipticals. The numbers in the color bars are the density of points. So as you can see here, we have a lot of points just a few points. But actually, we were able to kind of characterize it. So what is interesting here is that for the black line is the fit for each relation, while the white one is the fit for the total sample. So as you can see here, there is the fit for each morphological type moves a little bit below. So this shows us that the star-forming areas in earlier type galaxies actually are forming stars at lower rates. So that means that some sort of the efficiency of forming stars, it actually has a dependence on the morphology of the galaxy that is, that is on. So just a few numbers. The total amount of star-forming areas that we have is over 1 million. The vast majority of them live in galaxies that were previously classified as globally star-forming, and just a very negligible amount of them are in retired galaxies. However, the others, if we also take all the retired pixels or points, we see that around 13% actually live in galaxies that are globally forming stars. By the way, I know that if you zoom this too, it doesn't do the 100, but I can tell you why in the questions. So now, we can do exactly the same now per morphology. So as you can see here, it's something that we already saw in the diagrams, and it's expected. The vast majority of the star-forming areas or spaxels are in late-type galaxies, while a non-negligible amount of retired areas are living in late-type galaxies also. Why is that? Our feeling is that maybe these are actually in the bulges of these galaxies. However, we did not test it, but we can easily. So if we plot the retired areas in this diagram, what you will see is here. And this is why this is very painful. As you can see, the detection limit, this is the average detection limit. I think here is 1 sigma, 1 sigma. So every analysis that you may want to do with these spaxels is heavily dominated by this bias. However, it will be very interesting, but if we want to avoid this, probably we will need to only focus on this very little amount of points. So these are the residuals for the global relation and for the spatially resolved relation. And as you can see here, for the star-forming areas, for the star-forming galaxies and areas, those that are in the late types morphologies, basically you do not find like a major trend with this with the morphologies. However, when you move into earlier types, you see that this relation is actually going a little bit down. And for all the morphologies, in the case of the retired areas, we do not see a dependence with the morphology. But now you may wonder, why do we see a clear gap in this, between these residuals? Well, this is telling us clearly that there has to be some form of transition between the star-forming regime and the retired regime. That may be related, probably is what we think, with the consumption of the amount of the gas. So what we will need now is to try to have data about the amount of gas in the same regions. But that is something that we do not have right now for this sample. Also, something that will probably tell us some more information is to do this same study, but now with the dependence of the distance to the center of the galaxies. But that is work in progress. And then lastly, this is the density of star formation rate at a characteristic stellar mass. That is what you already saw in the diagrams, with dependence of the morphology. As you can see, the density of star formation at a characteristic stellar density is actually not the same. So this is basically what I have already telling you. We can try to know more about this when we do radial studies and when we know more about the gas content of the same areas. But that is something that unfortunately we do not have now. I can tell you that in MANGA there is an effort of doing a follow-up follow-up survey in which we are trying to observe the same MANGA sample, but with H1. However, this is still work in progress. I think now there are observations for like 1,000 galaxies, and maybe we can try to work with that, but let's see. So these are my conclusions. We see that we find the same trends that similar studies that does the same. However, all of us are finding different values for the slope and the scatter, especially the scatter may be important. I think that this may be due to the fact that all of these studies are not selecting the star-forming regions or galaxies in the same way. And that is probably what is causing these differences in the scatter. So we probably will need to try to test this with the same sample, which is actually easy. We just use the same sample and try to select differently and see if this has actually an effect on the scatter. Oh, sorry, probably I didn't say that. But this, the effect of the detection limit is actually very heavy. And actually, if you go to the low density, the low mass density, you see that there is some sort of bending in the data. So I know that there are out some works that are actually trying to interpret this. Our feeling is that this is just a bias effect of this, how close you are to the detection limit. So we are actually just avoiding to use those points and trying not to use them, not to analyze them, because we probably need to do more tests about that. And the rest is actually work that we need to do right now, is trying to see if we can find a sample, probably this follow-up by MANGA, in which we can try to have an estimation at least of the total amount of gas in the same regions that will actually tell us more about the interpretations that we're doing. And also, that is something quite easily to do, but we haven't done because we haven't got the time, is to do the same study, but now with a radial dependence. And that's it. Thank you.
Thank you. Since you were on time, you get a chocolate.
Thank you.
So, are there any questions? Yes, Sandro.
You showed this kind of average relation for all the galaxies. I was wondering if the galaxies also follow this trend.
Sorry?
So you showed basically, putting all the spaxels on one figure, right? I was wondering if the human galaxies also follow this trend.
That is an excellent question. That is actually something that we have to do. And there is a paper actually that was out like 2 weeks ago by Benedetta Vulcani, in which she does that for a much slower, smaller sample, but using Muse data, and they do not find the same. Actually, that is actually something that you should expect, because you cannot expect that all of your regions are forming stars at the same rate or with the same trend at the same distance to the center.
Any other questions? Maybe first from junior people. Okay, non-junior people. All right, let's thank Mariana again.